Okay, so hello everyone, thank you. I'm going to talk to you, to present to you a pretty straightforward set of open problems. It's going to be about closure properties of some model. So a model that we've been looking at lately is two-way one counter net. So two-way, we all know what that means. I mean, it's a model that can travel on the input tape back and forth. We have many models like that. And the one counter net is simply a labeled one bus, sorry. So a bus of dimension 1 with such that the edges are labeled. So just a brief introduction. Let's see what this model is good for. I mean, what it can realize that normal one counter net cannot. So this model can actually recognize A to the n, B to the n. Like exactly. It can recognize that the number of A's is the same as the number of B's, exactly, which is an unusual strength for VAS. Usually you can say something like the number of A's is as large, at least as large as the number of B's, but not exactly the same.
So you accept by state.
Sorry?
You accept by state. You
accept by state, that's right, yeah. Just briefly, let's see how to do it, just to get a feel of the model. So here is a word with A's and B's, A, and then B, B. And then this is the start marker, this is the end marker, this is all fairly normal. And how would we realize this language? So first of all, we read the word from left to right, and we gain 1 for each A, and then lose 1 for each B. And so at the end of the run, the value of our counter is, let's say that this is n. We read A to the n, B to the m. Initially, we don't know if they are equal. We would like to check. So after this left to right sweep, the value of the counter is n minus m, given that it is non-negative, of course. And then when we go back, we can gain 2 for every B, and then lose 2 for every A. So then after we transition back, the value of our counter is m minus n, given that it is non-negative. So how can both of these be non-negative? Only if n is equal to m. So that's actually nice. So we can realize this language, which is not recognizable by a normal one counter net. So this model generally has been studied before, and we do know, for example, that it is a really strong model. Even in the deterministic case, emptiness is already undecidable, so a really strong model. However, we do study various restrictions of the model in which emptiness is decidable, so there are interesting things to say about it. And one restriction that we talk about is what we call a sweeping two-way one counter net. What is a sweeping two-way one counter net? In such a model, the reading head is allowed to change direction only at the end markers. So you're not allowed to take 5 steps to the right, then go back to the left. You have to go all the way to the right, then all the way to the left, and so on. So that's some restriction that makes things interesting. So, okay, so what's open? So a few just closure properties. I'll draw a table. So there is just the normal two-way OCN. There is the deterministic case, two-way DOCN. And there's the sweeping, what I just described. Sweeping two-way OCN. And we have union, we have intersection, and we have complementation. Okay, so the deterministic case is actually understood pretty well. I mean, it has been shown, not by us, it has been shown that it is actually closed under intersection. And the intuition behind this closure is that you can use some nice tricks in order to zero the counter, in order to reset it. So you can do whatever you want to check in one of the components of the intersection, then reset the counter using some tricks, then check the other condition. So this is how it works. Again, this is not our work. It is also, this we have a formal proof of, it is not closed under union, it is not closed under complementation. And as for the two other restrictions or the two other models, it's actually completely open except for union, which is trivial as always. So, I mean, obviously, in any non-deterministic model, you can always have a closure under union, but both intersection and complementation are open, and we would appreciate any input on any of this. So, thank you.
Maybe one brief question. So do you have an example of a language which can be accepted by your two-way OCN, but cannot be accepted by just going back and forth?
Going back and forth, you mean once?
Just once forth and once back. That's my feeling, that it's a conjecture that every language can be accepted by just sweeping, can be accepted by just forth and back.
Well, maybe you have several letters and you want to check some conditions on the several letters about like.
So I would guess the common example you're offering is just A to the N, B to the N, A to the M, P to the M. So you have two of those blocks, and probably the first.
Oh yeah, okay. So you would need a few counters.
Like
Okay.
I guess something like that.
Yeah, thanks, Roland. That was that works.
So.
But do you have an example that separates sweeping from non-sweeping?
An example that separates sweeping from non-sweeping. We did have a few candidates, I remember, but we don't have a form. I mean,
we have an example. We don't have a constructive example, but for sweeping, the MTS is decidable, and for general two-way OCN is undecidable.
Right.
So that's
right.
but you can construct an example.
So we can differentiate by exactly what Shaull said, but a concrete language, we did have a couple of kind of candidates, but not something concrete. Yeah. Piotr?
I will ask a tough question. So why this is important? Why is this relevant? Like, is it important is this model appear in some other part of computer science or in math or in practice or wherever?
Okay, so
you can answer in green.
So look, I don't have a particularly appealing answer, but generally, I think it is interesting in general to take a well-studied model and to ask how it behaves when you can read the input data both ways. Anything better than that I don't have, unfortunately.
If Mikhail Latin is here, you would say it's a classic master watch. Well, master watch.
Okay,
okay,
so thanks, Asaf, again. Oh, you don't need.
I can keep it.
We have a lot of boards.
I see.
Richard, are you here? Yes. Do you want to give another problem?
I gave it a
Okay, sorry, I forgot. So is anybody else willing? Lorenzo?
Okay. Finish the projector.
Yeah, sure. Has anybody like HDMI, USB-C?
This started here, so should come soon. Okay. Colors are strange, but it's the adapter probably. Anyway, it's a bit psychedelic. But it would be good enough. So yeah, I'm Lorenzo Clemente from Warsaw, and I want to present a little problem. It's called the Restivo-Rathenauer conjecture, and it's a problem in a weighted automata. It's from the 80s. So the problem is about this notion of rational support. So what is a support? So the support of a weighted finite automaton is the set of words that the automaton maps to a non-zero value. And then the set of languages which are supports of some weighted finite automaton, this is called the set of rational supports. So this is a class of languages, and there is a nice bridge between quantitative world, which is the world of weighted automata, and the world of languages, which is a qualitative world. And it's a class that generalizes the regular languages. So every regular language, it is a rational support. In fact, it contains strictly more. For example, the complement of A and BM, it is a rational support. You can write with the finite automaton that has this as complement. And moreover, it's a nice class. For example, emptiness is decidable for rational supports, and universality is undecidable. And it has, there are closure properties. It's closed under intersection and union, but not complementation. Universality. Okay, so what is the conjecture? So this is the object of study. Is the object clear? Yep.
Is the notion of weighted automata the same as David explained yesterday?
Over rational numbers. Well, it explained two, I think. He mentioned at least two notions. This is weighted finite automata over a field.
Okay, but otherwise it can be any field, otherwise it's the same. So you like do one operation along the run and one...
Yes. So we'll repeat that, yes. So this is the same notion that David explained of any semi-ring. You multiply the weights along a single run. Then if you have many runs, you sum up what you get. And here, sum and plus sum and times are precisely the operations of rational numbers. So, for example, for completeness. And well, then there is a result by Rathenauer and Restivo that if a language and its complement are both rational supports, then in fact they are regular languages. So it's the proof is not difficult. It relies on what they call cancellation properties, and it's a kind of more sophisticated form of pumping lemma for weighted automata. And based on this result, they raise a natural question. Is it the case that if you have two disjoint rational supports, there is always a regular separator? And they posed this as an open problem in the 80s, and I checked, it seems to be still open. I mean, I couldn't find a solution to this so far. In the case of the alphabet being a single letter, this is true. It's an immediate consequence of the Lechmaler-Skolem theorem for linear recursive sequences, because in one-letter alphabet supports themselves are regular. So there is nothing to be done there. So the interesting story is when the alphabet has at least two. So this is the conjecture, which is an open problem. And this kind of separability results, which are unconditional, they are kind of common. I mean, I just mentioned 3 examples, other examples which are known to hold. Maybe the oldest one I remember is this result from topology. If you have 2 disjoint analytic sets, they're always Borel separable, Lewis-In's theorem. From computation, from computability, if you have 2 co-recursive enumerable sets which are disjoint, they're always recursively separable. And a more recent example, like half of the audience, there are many authors here of this result, if you have disjoint WST discoverability languages, they're always regular separable. And, so this is not a random kind of question. It's part of a pattern that appears in different areas, I would say, of computer science and mathematics. Okay, so do you have any questions?
Why do you call this unconditional?
Because it's always true. Because I think in computer science we have this habit that we want to decide things. So when you mention something, maybe we think first about deciding things. So these results where the decision problem is trivial because the answer is always yes, I felt like I need to qualify it. If I was speaking to a mathematician, I wouldn't have to say this.
How does pumping look, for example, in vector montage, or like a similar structure?
So the pumping for weighted, yes.
Like a pumping like result.
Maybe I can tell you offline. It's a more sophisticated form of pumping. It's like there's more alternation of how you split and what you can remove. It relies ultimately for weighted automata. It's a linear algebra argument. It's a dimensional. Yep.
So I don't know if Pascal already asked this, but what role does the field play? So do you, can you get every language just by taking the rationals, or do you have to consider weird fields?
Actually, I don't know. So this was posed, I think, for the rationals. I don't know if the actual field, how much of a difference it makes. I could imagine finite fields may behave differently, for example. But I don't know.
So you mean for every field there is a disjoint conjecture?
Yes. Well, I would expect fields of characteristics 0, they're sort of the same, because you cannot really distinguish them in this setting. So
do you know about people thinking about this conjecture, or you thought by yourself about this?
I didn't think much myself about this. I saw it's an interesting problem, I think, and I have not seen it mentioned anytime recently. It seems to be a nice conjecture, but I suppose they haven't forgotten. This is my feeling. Maybe it's a good time to revive it.
Is there any class that is known to separate them, like CFL or something?
Say it again?
Can the two rational support be separated by CFL?
Yeah, I don't know. Yeah. They seem to be incomparable. For particular example, CFL, it seems, even though the example I gave suggests some counting. So more generally, for motivation, this problem is about what's understanding the structure of supports of.
Any more questions? Okay, so thank you, Lorenzo. Does anybody else plan to use slides on these sessions? On this session, no.
Depends if you're doing the future, the Pythagorus stuff.
Yeah, but okay, not immediately, right? Okay. Are there any other open problems for now?
Yes, yeah,
right. Is it okay for camera?
Yes.
So thanks for the proposition of presenting some open problems. It's about so it's related to some problem called the home space problem. When you have a verification problem, like you would like to prove that something is you don't have a bug in your system, sometimes it's reduced to a reachability question. So for Petri-net, it's like, is it possible to reach a bad state? And we can solve that problem. But sometimes you would like to see if your system is good, meaning that whatever the behavior of your system you have, there exists a way to take the control of your system at any point and to reach a good configuration. This is what we call the home space problem. And we recently discovered that in order to solve that problem, so we find a way to solve the problem, But in order to solve the problem for Petri nets, we need to solve another problem, which is called the universality reachability problem. And the problem is defined like a reachability question, but the question is it true that any configuration is reachable from an initial configuration? Okay. So the problem is take as input a Petri net, a set of initial configurations, given, for instance, as a semi-linear set. And the question is, does the reachability set is the full set of configuration? So that problem is decidable just for the following reasons, just because we have two semi-algorithms deciding the problem. Either, so you want to know if the reachability set is the full set of configuration, let's say n power d, if you have d counters for a Petri net. The first things you can do is you can check if the reachability set is semi-linear, and we know that this problem is decidable, so you check it. If it's not semi-linear, for sure, the reachability set is not the full set. And in parallel, you can check if there exists a configuration that is not reachable. Okay, so you can launch the two algorithms, and in fact, at some point, you can decide if the reachability set is semi-linear. You can compute the reachability set, so you can check that okay, it's really the full set of configuration, and if not, you will find a witness proving that it's not universal. So the open question is what is the complexity of the problem? How to decide efficiently that the reachability set is the full set of configurations? So with some colleagues, it was maybe 4 years ago, we showed that if you start from an initial configuration, okay, so if you want to know if the reachability set from an initial configuration is the full set of configurations, we proved that this problem is X-space complete. Somehow it's similar to a coverability question, even if we solve it using some techniques about mutual reachability questions in order to solve that problem. And the open question is what is the complexity in general, starting from a semi-linear set? Is it Ackermannian, or is it it's at most Ackermannian, because we have some new results explaining that from Roland. But the question is it below Ackermannian complexity? Is it X-space? And maybe rather than starting from any semi-linear set, the problem is still open if you have not just one configuration, but two configurations. Okay? So you have two configurations, and the question is, does the reachability set, starting from those two configurations, is it the full set, the full reachability set? This problem is difficult because it's quite possible that the reachability set from that configuration is a very complex set. The same from this one, but when you make the union of the two sets, the area where the set is very complex can disappear due to the union, because you are going to hide some complex structure thanks to the reachability set of the other point. Okay, so this is the problem. What is the complexity starting of the universal reachability problem, starting from two configurations, and it's related to some on-space problem and some problems about formal verification for Petri nets. Thanks a lot.
Can't encode these two initial configurations into one? There's initial choice between these two.
It's not. I mean, if you have just one configuration, there is something that occurs that is really good if the set is universal. And in particular, those configurations are reachable. Okay, all those configurations. So if you take, if you add to your Petri net, you add an action that can go in that direction, that decrease the counter in that direction, you will see that the two configurations will be mutually reachable. So in particular, there exists a small run, and you will prove that if the reachability set is universal from one configuration, then there exists a short run, maybe that's not going to that configuration, but maybe a little bit later. And you have the same in this direction. So in particular, the reachability set is something like an upward closed set, because you can go in the two directions. So it's like using a classical well-quasi-order, upward closed set, computing by saturation techniques, or computing by some kind of pre-star computing the reachability set, you can decide the property. If you start with two configurations, the main problem is the following one.
It's important that it's a Petri net for
It can
for
be,
bus with
no, it
states.
can be the same, yes.
You can
for
encode
bus.
it, right?
Yes, you can. It's not so clear. I mean, that
If
you
you
can
just add-
reduce one problem to the others.
If you just like, if you have two starting points, you just add one new state
Yes.
with another state,
Yes, but you need to.
and you go to these two initial states.
Yes, but for the universality, you need to come back. You need to be able to come back to the initial configuration.
Aha, so in the
Cover
same
everything.
configuration in which you start. In
All
the
the
same state.
configuration, yeah, all the configurations must be reachable. So it's not so clear how to reduce one problem to the other, even if we think that I think that the problems are equivalent somehow. The complexity should be the same. Yes, the problem is that in that case, if you have two configurations, it's possible that configurations that are here are reachable, in fact, from that one. And configurations that are here maybe are reachable from that one. Okay. So in particular, you have a cycle, which is good in that case. It means that you have a way to add some points in some directions. But maybe it's not, symmetrical for the other one. I mean, you don't have a, we don't know how to solve this. But I guess there was.
Do you have a solution for linear sets? For linear sets, so you have
So
periods.
if you have just one linear set, you can encode the period into your vector addition system, which is okay. The main question is if you have two linear sets or 2 points. Yes.
Can you say anything about the set of configurations from which you can reach everything? Do you know that it's linear or something?
The set of configuration, you mean if you start from one configuration, which configuration are such that if you start from that one, you get the full set? No?
Yeah, which are the configurations such that if you start from them, you get the full set?
No, I don't know.
Any other questions? Okay.
If you have some ideas, I'm
Thank you,
interested.
Jerome.
Yes.
Anybody else willing to give another problem? Sylvain, you don't want to present this XP stuff? Maybe you want to present this XP stuff? Sounds interesting.
It's a question related to Michal's question.
Sorry.
So
Yes.
it's about fixed parameter tractability. So Michal was saying, oh, one very natural parameter will be just the bus itself. So is it the case that if you fix the bus, then you can get some, in the complexity, some computable function in the size of the bus times the size of your instance and the size of your instance is just the input and output. But here, with the parameter, the dimension. So this is something very used to, right, in BAS, because this dominates the complexity very often, and the question will be coverability. Now, we know, thanks to recent results about coverability, that there are some conditional lower bounds that tell you that you cannot do better than something like n to the 2 to the d, right? Assuming ETH. No better than this kind of complexity. And I was wondering whether you could forget about ETH and sort of show that you cannot do better than something like this in general. So my question would be very precisely, can you show that coverability parameterized by dimension will be x space hard. So if you don't know, this is an analog of XP. XP will be the time version of that thing, which is saying essentially that you have something in n to the some parameter, some f of your d. That's essentially what XP is saying. And this is the time version, but it will be the space version of that complexity class. So what's good about XP is, in particular, XP is known to be different from FPT. The delta separation here is not conditional, unlike many other things. So, and in particular, if you show a XP space hardness, then of course you're definitely separated from FPT. So that will be one way of doing this. I don't know, I suspect this might be doable. I suspect that Michał's question is very hard. I suspect this one is actually doable, that we sort of have the kind of ingredients we need to do that, but one obstacle is just that this class is just not known. I mean, I couldn't find any literature about this stuff almost. It's not well known at all, so characterizations of the kind of problems which are XP space hard and so on, essentially you would have to go back to basics like Turing machines and stuff like that. No easy way out of this. But otherwise, I would expect maybe this is doable. So that was a proposal to show that there's no FPT in dimension for covariate. That was a suggestion. Yeah, there will be future directions later, right?
Yes.
So I can talk about future directions later. Okay. Any questions?
Yes.
How do you exactly define XP space?
You take the complicated definition of XP and you take space instead of time. Because I don't know it by heart, the definition is not so simple. But
this is not just space n to f of d, or is it deterministic space n to f of d, or?
I suspect probably something like this. I think it exists in the literature, this class, but I found like one paper that talks about it.
Yeah, there are papers considering like space complexity classes.
But it's not very common, right?
Yeah, it's not very common.
Probably you know a lot more than me about this. So.
I have a question. Yeah, when you are looking at complexity classes, sometimes you would like to have some, it's complete or hard for some reductions.
Yeah.
In that case, what are the reductions?
Yeah, you have those parameterized reductions that take into account what happens to the new parameter and what you do with the pure instance itself. So it's
okay.
You need to be careful about what happens to your parameter.
All right. Thank you so
Thanks
much. I don't see anybody on the list more, but maybe there is somebody still hiding. So I propose, so we still have 20 minutes on this session, I propose we can talk a bit about progress. So like about closed problems. So yesterday I posed a conjecture about this root of vast language. So it turns out that conjecture was false. So it turns out it's worth to mention your conjectures on such workshops. So group of many people with Georg, Łukasz, Roland, and others falsified this. So I would like to tell you what is the counterexample. And well, is it the end of a story or not? And I hope it's not the end of a story. So just to recall, very briefly, so root of language L is just set of words such that there exists some number k, such that just repetition of k times of w is in the language L. Yeah, so my conjecture from yesterday was that the root of vast reachability language is vast reachability language. And that's not true. So the example of a vast language, such that the root is not a vast language, is the following one. it's over two letters, A and B, and it's the following words. So first you have B, some number K of B, then you have A, and then you have something else, like A, this ends the last block, and then you have something, some W, some rest, such that the length of this initial block of B is exactly equal to number of A's in the rest, so included this A, right? Okay, so I hope the language is clear. Number of B's in the first block equals number of A's in the whole word. So it's clearly a vast language because it's one counter actually is needed, and it's deterministic. You just increase the counter on this first block, and then after this first block, you decrease the counter on each A, right? And you accept by 0. It's actually deterministic, and it's actually already an integer vast language. So actually, and you can see what is the root of L. Root of L may be intersected something like B plus, A plus. Yeah, like to ignore some pathological cases. So we can see that, like, if you are in the root, so let's say that you are aware like B, K, A, M, and into some power L, you are in the language L, right? So what it means? So it means that number of B's in the first block, so K, equals number of A's in the whole word, so M times L, right? And there exists L, if and only if there exists L like that. So what is this? K, if there exists L such that K equals ML, so it's actually equivalent to L being, M being a divisor of K, right? So actually the root of language L intersected with words of the form B star A star. That's exactly words in which the number of A's divides the number of B's. And it's pretty easy to show it's not a vast language, I guess you have an intuition that division cannot be actually implemented by vast. There is an easy proof, but I will go into that. So yesterday I said that we almost have a proof that my conjecture is true for deterministic integer vast languages. And you actually have a counterexample. So the almost word was important. So it seems that our proof was not our almost proof was not a proof. But so what was our motivation? Maybe I will briefly recall you. So I told you that we would like to solve the following problem. So given two vast languages or integer vast languages or whatever, K and L, I would like to answer whether there exists a word W and numbers K and L such that W to power K is in this language K, and W power L is in the language L. So actually, whether root of K and root of L non-empty intersect, right? So the idea to solve this was actually to show that root of vast is a vast, and then you just intersect these two roots for two vases for roots, and then it would give an algorithm. But this doesn't work, as shown here. But I think, I hope, I think we have a proof that this problem is actually decidable for deterministic integer vast. And I hope this is true. It's not written down. So the conjecture is then like the next step, maybe not so immediate now, is what about K and L being vast languages? Is this problem decidable? Or maybe we can exploit these examples to show undecidability. So I think if this problem is understandable for vast reachability languages, maybe tomorrow I can have another update about some other group of people showing undecidability. So that's for it. Any questions or remarks? Lorenzo?
It would be interesting to see if there are nice classes of languages which are close on the root. Like we know that the regular languages are.
Yeah.
In the commutative setting, we know that the semi-linear sets are.
Yes.
Is there anything like non-finite states?
Yes, I think it's an interesting question. Yeah. Some other remark, questions? Okay, so thank you. Is there any other update? I know there was Shaull.
It's mostly Michal update, but
I will change the board. Or it's not much better.
So we had the box reachability problem, remind you, where we have we have a VAS, we have one VAS, no states. Then we start configuration 0, 0. We have some target configuration XY, and we say that XY is box reachable if there is a run that starts from 0, 0 and gets to XY, but does not go outside of the XY box. So the run stays entirely inside. And the question was to show, or the conjecture was that for all points that are deep enough in the first quadrant, so after some outside of some L shape here, the set of box reachable configurations coincides with the reachability relation, or the reachability set from 0, 0 of the one VAS. And we worked on this a couple of months. It took me about 20 minutes to I don't think I'll go over the entire proof. I'll just mention the techniques. So the idea of this, we know that for
the answer is yes or no?
the answer is yes. Yeah, the answer is good remark. So the answer is yes, and the idea is the following. Basically, we have two tools to solve this. One is the Steinitz technique that shows that if there is some run from 0, 0 to XY, then there is also a run that stays within some reasonably width. The width of this sausage, let's call it, is dependent only on the VAS. And if there is a run from 0, 0 to XY, then there's also a run that stays in this lane. So this is almost solving box reachability. The only problem is what happens when you're very close to the end of the sausage in this part and in this part. Maybe the run goes through here and then it's not box reachable. So what Michal added to this was a lemma that they have. Says intuitively that if you have a set of vectors, suppose the VAS has this vector and this vector, and you look at the cone generated by these two vectors, then if it covers the entire first quadrant, you can say the following. For every point that is deep enough inside the cone, so let's say xy is deep enough inside the cone, the real cone, the real coefficients, so every point that's deep enough inside is reachable in z positive if and only if it's reachable in the lattice z. And the way we use this is that now instead of trying to reach xy directly from 0, we can start by taking some positive vector, repeatedly applying it until we're far enough from the edges, and taking it backwards from xy until we're far enough away from, again, the edges. And this drawing is very bad, but imagine that this point is very low into the left, and this point is very high into the right, despite the picture. And once this is the case, then we can use the Steinitz path here, and there is no danger that this sausage will go outside anything. It's kind of a rough idea. I think the ugliness of the drawing reflects how complicated this is. Yeah.
What was
answer this more precisely than it? Do you want me to just state the lemma, or do you want me to say the lemma? The lemma says the following. So we called it deep in the cone lemma. Make it sort of self-explanatory name. So you've got a set of vectors D in Z to the D.
Finite.
Finite, yeah. Then it naturally spans the following three objects. First, I will define the cone R of D. Yeah, so these are just non-negative combinations of D, of vector from D. So there is a
R plus.
Yeah, cone R non-negative. There is a integer cone, integer non-negative cone. These are just integer non-negative integer combination. And then there is a lattice. Let me write it like that. Lattice Z of D. These are just integer combinations, possibly negative. Yeah. So clearly, you have that the non-negative cone, non-negative integer cone, is contained in the lattice intersection the real cone. Yeah, but this is not necessarily strict, because there may be some points that are reachable by non-negative coefficients. They are reachable by integer coefficients, but in order to reach them by integer coefficients, you need to take some of them negatively. Yeah, and then the lemma says that there is a number m depending only on the set of vectors, such that for every point x which is inside the real cone, at distance at least m from sides, from say boundary of the cone, yeah, to test whether it is non-negatively integer reachable, it suffices to check whether it is in the lattice. Yeah, so the picture is that somehow you've got here the cone, the real cone, yeah, and now you've got also the lattice. Let's draw it like that. And if you look at the part that is here, then exactly the intersection of the lattice with the part here is what you can non-negatively reach. Yeah. So sort of this kind of Frobenius type aberrations appear only on the border near the boundary of the cone. Yeah, that's the lemma.
Any other updates? So I can give a quick update on Min+. It's due to Shaull, who said whilst I was doing it, isn't it p-space hard for Min+? And the answer is yes, it is p-space hard for Min+. So suppose you have NFA universality. So you have a NFA. Not there. You don't like that. It's okay. Suppose you have an NFA with that you want to know whether you accept every word, and you have some states which you're accepting, and from those states, on a hash, you're going to go to a part of the automaton that just reads every letter with weight 0. So inside the automaton, I'm going to turn this also into weighted automaton where every edge has weight 0.
Could you recall very briefly what was the conjecture?
So we're going to ask what is the complexity of deciding if this thing is unambiguizable. Does there exist an equivalent unambiguous thing? So already what can we see? If you read a word that looks like some word from the NFA followed by sharp, followed by anything, if W is in the language of the NFA, then this word maps to 0. Okay, because every transition I added was of weight 0. If from a non-accepting state, I'm going to go to a different part of the automaton, where I'm going to do something that is A with 0, B with 1, and A with 1, B with 0 in different states. Okay, so now if we're going to use these runs, well, if there was also a run to an accepting state, followed in this state would be better because it's of weight 0, because all of these runs have higher weight. So these will only be the maximal runs, sorry, these will only be the minimal runs if the word was not in the language. Okay? So in these cases, if there's a word that's not in the language, then this word followed by A, N, B, M, well, the weight of this should be equal to the minimum of N and M. Okay, so one of these is minimum of N's, one of them is minimum of N's, and, well, basically, you cannot do this with unambiguous, right? You're going to need one run to track the number of A's and one run to track the number of B's, and let the automaton decide which is minimum. So basically, this construction is, well, it reduces NFA universality to whether this automaton is unambiguizable. Okay, so if the NFA is universal, you'll never use any of this, and you have the 0 automaton, definitely unambiguizable. If the NFA is not universal, then there's a run that definitely needs, there's a word that definitely needs at least 2 runs. Okay, so the problem is still open, and this sort of trick I don't expect to work for the field of rationals. So min plus, probably you shouldn't try going beyond p space. I mean, you could try, but I wouldn't bet my life on this, but still, for plus times, wildly open.
You bet it.
I would bet it's harder than NL, which is the best I have so far.